So we've just worked through this transitive closure problem from the worksheet. And as we go through all these different ordered pairs, it turns out we have to keep adding and adding and adding until actually it turns out that RT is all of A cross A. We actually need to have everything, and we had to add all these elements. And you can see why we had to add them, because we were, crossing over. Yeah, sorry I didn't start recording earlier. Does anybody else have any questions on that? Angela, do you understand now that we already had the 1-1?
Yes, I understand.
That's good. So this was a big one. I won't give you one that's that big. We did one in class that wasn't that big. All right, so that's part A of number 3. Part B and C and D, we are asked to construct binary relations on A that have specific properties or do not have specific properties, right?
Yep. The first one was a binary relation on R2. It's not reflexive, not symmetric, not transitive.
We want to construct a binary relation. We're going to call it R2.
On A, sorry, I forgot that part.
Yep. It's going to be a subset of A cross A. And we want it to be not reflexive, not symmetric, and not transitive either. Right?
Yep. So for my set, I put 1, 4, 2, 3, and 4, 2.
So you put 1, 4.
2, 3, and 4, 2.
And I'm just wondering, why did you put 2, 3 in there?
The 2, 3 was so I thought I had to use all of the elements in the set. Is that true or no?
Nope.
Okay.
This is a subset of A cross A, isn't it?
Yes. Oh, okay.
See what I mean? So yeah, and so it's not reflexive, right?
Because 1, 1, 2, 2, 4, 4, and 3, 3 aren't, or 3, 3, 4, 4 aren't in there.
Even if just one was missing, it would be enough.
No, I should have. I mean, that actually would have been more work.
I
But I
mean,
think
so you could add a couple of those. You just can't add them all. And it's not symmetric, right?
because 1, 4 is in there, but 4, 1 isn't in there. And then 4, 2 is in there, 2, 4 isn't in there.
Yep. But it's enough for it to fail for just one. So you can just say, you could just say 1, 1's not in there. And then you can say, 1, 4's in there, but 4, 1's not in there. And that's enough. You don't have to say both. See what I mean? Like, I don't want people to feel like they have to say more than they have to say, because it just takes more time. You don't have to verify every single way that symmetry fails. Symmetry is a universal property. It has to be true for all elements, little a and little b in set A.
All
So
right.
that's enough. And then what about not transitive?
1, 4 is an R2, and 4, 2 is an R2, but 1, 2 is not an R2. So it's not transitive.
And that was exactly why you put the 4, 2 in there.
Mm. But yeah, the 2, 3 wasn't necessary in that.
But you could add it. It doesn't make it wrong.
Well, yeah, technically, but
So, another possible solution would be what you said, 1, 4, 2, 3, 4, 2. It still works. It still fails. Because we got 3 different ways to show that it fails symmetry.
True.
Questions, anybody? So for C, we wanted to make a binary relation R3, right? And what were the properties that it needed to have?
Sorry, you cut out for a second. What'd you say?
So for R3, it's a binary relation we need to build. What are the properties it needs or doesn't want, or that we don't want it to have?
Not reflexive, but symmetric and transitive.
Okay.
All right, for my set, I have 1, 2, 2, 1, and 1, 1.
1, 2, 2, 1,
And
and
1.
1, 1.
Yep.
But that is not transitive.
It isn't?
Because if you put the 2, 1 and the 1, 2 in the other order,
I didn't even think about that.
yeah, we got to think about that.
So it would have to be an extra, it would have to be 4 elements.
Yep, that'll work.
1, 1, 2, 2.
Mm-hmm.
Oh, you already have it there. Okay. So if you're verifying it's true, like transitive or symmetry is true, would you have to do every single example of it being true? And then for the false ones, you only do it one time because it proves it's false?
Yeah, but there is sometimes a smart way to verify um, like that it's symmetric without going through as much as you think. First of all, it's not reflexive because, say, for example, 3, 3 is not in there. That's all it takes, you know.
Okay.
It is symmetric because we can group the elements with their symmetric twins. 1, 2 is in R3 and its twin 2, 1 is in R3. And these are the only elements where the first and second coordinates differ from one another. So this is the only set of ordered pairs where we have to check symmetry. We don't need to check symmetry for these little ordered pairs where the first and second coordinates are the same because, of course, symmetry is never going to go bad for those.
Okay.
Transitivity, yeah, 1, 2 is in R3 and 2, 1 is in R3 and we have 1, 1 in R3. And then 2, 1 is in R3 and 1, 2 is in R3. And we need 2, 2 to be in R3 and it is. So this is nice. You don't want to build a bigger relation than you need because it just takes lots and lots of time
Prove it's
to
true.
verify stuff if your relation is really big.
Okay.
I just want to point out, and there's another possible solution. The empty set is technically a subset of A cross A. It's got no ordered pairs, and it is symmetric and transitive by false hypothesis.
That actually goes to E.
Mm-hmm.
I actually, is it fine if we jump a little bit ahead?
Yeah, let's go ahead
Because
and jump to
I wanted,
E. So
all
we
right.
could write this: Y is the empty set symmetric and transitive. So let's go to E.
The way I explained it was if I feel like this is going to make sense. If it was written as like an order pair, so if it was empty set as an order pair to help you kind of read a little bit better, and it wouldn't be reflexive because 1, 1, 2, 2, 3, 3, 4, 4, none of those are in there. But it would be symmetric because it's empty set, and then the mirror, the opposite of that is empty set, which are technically
Yeah,
both.
but that's
Does that make sense?
yeah, but that's not quite right because
Okay.
the empty set has no ordered pairs at all. There's not an ordered pair in there that's empty set, comma, empty set. There's
Okay.
no ordered pair in there at all. So let's just recall the definition of symmetry, right? R is symmetric means for all elements little a and little b in the underlying set A, if AB is in R, then BA has to be in R, right? So
Yeah.
this is like if P then Q. So that has to be satisfied in order for symmetry to hold. But there is no ordered pair little a comma little b in the empty set.
So they're
So
both
the hypothesis
okay.
of symmetry fails because AB element of the empty set is false. So symmetry holds by false hypothesis.
Keep forgetting that it goes all the way back to truth tables
It
and if P
does.
then Q.
There was a reason for all that.
Okay.
And same thing with transitivity. Let's just recall the definition of transitivity. It's an if-then definition as well. See, the definition of reflexivity is not an if-then definition, but R is transitive. Means for all little a, little b, and little c in A, we know what it means. If AB is in R and BC is in R, then we need A comma B to be in R. This is the hypothesis. But there is no AB in R, and there is no BC in R.
So it's also true by false hypothesis?
Yeah,
Okay.
there is no little a, comma, little b in the empty set. And there is no little b, comma, little c in the empty set. So transitivity holds by false hypothesis.
Okay.
So the empty set is actually kind of handy when it comes to transitivity and symmetry.
So does Q turn into A, comma C,
Ah, thank you.
Professor?
Thank you. Sure does. You can tell I've been doing math all day and I am tired.
I didn't realize that either.
Yeah, I had like a 2.5 hour office hour this morning, and I've been working on building tests all day. I am tired. Okay, good. So we got numerous people in the room. Who's got a question? Email me if you want a point of extra credit to be added to your homework, Angela.
I'm looking at these other ones. I'm not very confused on them, but I don't think I have to go over all of them.
Well, I mean, if nobody, I mean, I'm just waiting for anybody to ask a question. If you've got a question and nobody else is asking.
Can we work on number 6?
Number 6?
Yeah.
Sure, let's look at number 6. So we went through a problem very similar to number 6, where we used 4, but here it's congruence mod 2, not mod 4. And it's a binary relation on Z. And it's defined like this: for all integers, little a and little b, A is congruent mod 2 to B if and only if 2 divides A minus B. And so the way to think about this is it splits the integers up into 2 different sets based on the remainders, right? Because when we're dividing by 2, the even integers give us a remainder of 0. Whereas the odd integers give us a remainder of 1 when we divide them by 2. And what congruence mod n says is elements of Z are congruent mod n if you can get between them by jumps of size n. Well, look, we can get between all of the even integers by jumping by jumps of size 2, right? You can get to any of them from any of the other ones. 2 divides the difference between two even numbers. So all the evens are related to each other. And the odds are 2 apart from one another. You know, jumps of size 2. You know, it might be 8 or it might be 10 apart or it might be 12 apart. But you know, the difference between any two odds is divisible by 2. And so what congruence mod 2 does is it groups the integers up based on remainder. So for part A, we want a positive integer A B, my bad, such that zero is congruent mod 2 to B. There are lots and lots of positive integers that are congruent mod 2 to 0, namely all the positive even integers. So you could put 2 or 4 or 6, right? Where you
Oh,
can
yeah.
see what I mean, or 4
Oh,
or 6, you know, any of these. And B says you want a positive integer A where A is congruent mod 2 to negative 12. Well, it's still, we're looking for a positive even integer. So it's still, you know, 2 or 4 or 6 or 8 or, you know, any of these. 0 is not positive or negative though, so 0 won't work. C, we want a negative integer B such that 1 is congruent mod 2 to B. So can you give me a B that's negative, that'll be congruent to 1, Anticott?
that's negative, you say?
Yeah, negative integer B, such that 1 is congruent mod 2 to B.
-1?
Yeah, or negative 3, or, you know,
-1.
right? Any
Okay.
odd negative integer. You get the idea?
Yeah.
And then I think I meant to ask for a positive integer B, but whatever. I think I didn't do that quite right, but D, you know, you could do that one. But part E says find the equivalence class of 0. Well, the equivalence class of 0 are all of the integers that are congruent mod 2 to 0. Well, that's all of the even integers. Any of the evens are congruent to any of the other evens. 0's even. The congruence class of 1 is all of the odds, positive or negative. And then I think I asked you to find the partition. I didn't ask you to find the partition, but we could find the partition.
Yeah.
I think I asked you to do it for congruence mod 3, but the partition congruence mod 2 induces on Z is this. The partition is the set of the, with these two groups of integers. That makes sense?
Yeah. Thank you.
So we don't, mod 2 is one game to play, mod 3 is a game to play, mod 4, mod 5. Other questions? No other questions? You finished your WebAssign, folks? Have a good night, Nick, and don't forget to email the testing center.
Don't worry, I already got it ahead. I called them
Good,
right before they closed and I got it in for
perfect.
Monday.
All right, great.
Have a good night.
You too.
We continue working on the chapter 8. So anybody don't know.
Hello? From 8.3 from WebAssign or
No, this one, the
the
question.
worksheet? Okay, and also Angela's asking to work on 8.3 from WebAssign. So do you have a specific problem from the worksheet? Anacott, have you had a chance to work through these yet?
Yeah.
Yeah,
Yeah, I did work through some of them, but I didn't finish
I can't understand what you're saying.
it. Really, can I hear me?
Yeah, I can hear you, but I cannot understand what you're saying. Do you have a specific problem that you worked through and you didn't know how to work?
I want to work like on number 2, actually. So,
Okay, we'll do number 2 and then we'll go to WebAssign.
okay.
So these are these properties, reflexivity, symmetry, and transitivity.
Yeah.
So we're given S, and it's got little a, little b, little b, little c, little c, little c, little d, little d, little c, and it's got e, and so is curly S reflexive, Annika?
Yes, we have A.
Not enough. You have to have AA, BB,
I'll say from, yeah.
you have to have all of them. How many ordered pairs are required for reflexivity to be satisfied? You have to have one for each element of X. You have to have an ordered pair for each element. It's not enough that we have AA. We need BB and CC and DD and EE. So which one's missing?
DG, so it's no.
Yeah, DD is not in S. So it's not reflexive because all it takes is to be missing one of those required ordered pairs for reflexivity to fail. Okay?
Okay.
Is curly S symmetric?
No,
Okay, so why not?
we only have like ED and DC, like we don't have AB,
We don't have to have AB.
so it's fine.
It's an if-then. If
Uh,
we had AB, then we would need BA. We don't have to have AB and BA and AC and CA and AD and DA. If we had to have that, we'd have to have all of X cross X.
Okay.
It's if you have an ordered pair, little x comma little y in S, then y comma x must be in S. It's an if. It doesn't say you have to have little x comma little y. It says if you do have it, then you have to have the symmetric twin yx. So let's look and see what we've got. AA is in there. Well, AA is in there. So, I mean, you know, these little pairs that are the reflexive pairs where the first and second coordinates are equal, they are never going to make
Okay.
symmetry fail, because if X is equal to Y, then we've already got YX in there, you know?
Mm.
But then we look at the pairs where the coordinates are different. CD is in S and its symmetric twin DC is in S. So it is symmetric. Those are the only pairs where the first and second coordinates are different. Those are the only pairs where you have to check symmetry.
Okay.
Okay, what about transitivity? So we're looking to cross over. We're looking for crossover elements. If XY is in S and YW is in S, then we need XW in S. Okay, so we're checking to see if we have this hypothesis satisfied for any pairs XY, YW. So do you see any pairs where we have the same coordinate for the second coordinate in one pair, but it's also the same coordinate as the first coordinate in another pair?
So we can do CC and the CD.
Well, you don't ever have to use CC, because if you are checking CC against
Yeah.
CD, right, we have CD because it's right there. So you don't use these little reflexive pairs to check transitivity either, because they will never make transitivity go bad. You use ordered pairs that have different first and second coordinates, like CD is in S and DC is in S, right? So that's the hypothesis of transitivity satisfied, right?
Yeah.
So we're crossing over on the D. What do we need to have in S? Since we have CD and we have DC, what is the order pair we're looking for?
G.
Pardon?
So
When we're crossing over on this D, the D is the Y, X is C, W is C. What's the order pair we're looking for?
CC. Yeah.
And do we have CC?
Yeah.
Okay. But these two order pairs could be written in the other order. If we write it in this order, we're crossing over on the C. What do we need to have in S?
D.
Do we have DD in S?
No.
So it's not transitive. I guess I'll write it in green the same way that I wrote it. That makes sense?
Yeah.
Okay, Angela, let's go to WebAssign. Hang on just a second. 8.3, did you say? Angela? 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 Huh, I don't know what to do. Angela, are you there? Well, Auntie Cot, Angela's not here. Do you have any other questions? Angela, where are you? I'm going to send her a message. Auntie Cot, do you have any other questions while we're waiting for Angela to come back? Can y'all hear me?
Yeah, I can hear you.
Well, I'd appreciate somebody saying something. Do you have any other questions? Angela, if you're, we're waiting for you to come back. But in the meantime, Auntie Cot, do you have any other questions?
I wanna work on number. You already work on number 4, so number 7 is the one we did in class. Let's work on number 4. This.
Number 4
Yeah.
from the worksheet?
Yeah.
Okay. Angela, let us know when you get back. So it's a big relation that I gave you, and you're supposed to group together elements that are related to each other. Those are going to be the equivalence classes of the equivalence relation, okay? So,
Excuse me, I was in the bathroom.
hi, Angela. All right, so let's go to WebAssign. Was there a particular, I'm going to share my screen here in a minute. Was there a particular problem that you wanted to look at?
Yes, I want to work on number 2.
Okay. Uh, All right. So number 2. So this is congruence mod 4, Angela. And we worked extensively on congruence mod 4 in class, okay? That's what, this is the definition of congruence mod 4, but instead of having it on all of Z, they've restricted it to a small subset of Z, just the integers between 1 and 24. Do you see that?
Yeah,
So we want to find the equivalence class of 1. Now, what is the remainder that we get when we divide 1 by 4? In other words, we want to look at the number line and think about jumps of size 4, okay? So if you draw a number line, every fourth element is going to be related to each other, okay? So instead of every second element when it's congruence mod 2, or every third element when it's congruence mod 3, it's every fourth element is related to one another, okay? So what's the next element in A that's going to be related to 1? In fact, 1 is definitely in there, okay? 1, because doesn't 4 divide 1 minus 1, Angela?
yeah,
Because 1 minus 1 is 0. 1 is definitely going to be in its own equivalence class. That's one of the things that's always true about equivalence classes is the representative. And here we call 1 the representative of that class. It's going to be in its own equivalence class, right?
yeah.
So, for sure 1 is going to be in there. Now, let's think about some other numbers from A that are going to satisfy 4 divides 1 minus that number, okay? Well, it's going to be numbers that we can get to from 1 by a jump of size 4. Like what's the next integer in A that leaves a remainder of 1 when you divide it by 4? Because that's the way this grouping goes. They're going to be related if they have the same remainder when you divide them by 4. That's why 4 divides their difference. Like, think about 5, okay? Think about 5. Let's let X be 5. Let's let Y be 1. What is 5 minus 1?
4,
4. Does 4 divide 4?
yes,
Because, of course, 4 divides 4. So, see, 5 is separated from 1 by a jump of size 4. 4 will divide their difference. The space between 1 and 5 is a distance of 4. 4 divides that distance. That's what X minus Y is talking about. X minus Y is the distance between X and Y. Does that make sense?
yeah.
All right. What about the next number that'll be related to 1? Will be in the equivalence class of 1 or the congruence class of 1.
Would it be 9?
It would be. because you think about it. 9 minus 5 is 4. 4 divides 4. 9 minus 1 is 8. 4 divides 8. So 1 and 5 and 9 are all congruent to one another mod 4 because they're jumps of 4 apart. Does that make sense?
Yeah.
And you can do that for all of those. And look what happened. So, I mean, there's more stuff in here. Okay, that's not all that's in there, but there's more. I mean, you keep going all the way up to, whichever of the ones between 1 and 24 that there are. I don't know what yours says. It might not say 24. It might say 23 or 22 or something. I don't know, right? Because this red number could be different for different people. But 5, the congruence class of 5, well, it's the same as the congruence class of 1 because they're related. 1 and 5 have the same congruence class. So what would the next number be that's in both of these?
Would it be 13?
Yeah, 13 is going to be in both of these. And what would the next number be?
17?
Yeah. Their congruence classes are the same because they're in the same 1 and 5 are in the same class together. That means their classes will look exactly the same. All right. What's the next one?
21.
And that's it. Because the next one would be 25, but that's not in there, at least for mine. I don't know what yours says, right? But you go up as high as you can. But what about the equivalence class of 2? Let's work on that. All right. Well, 2 is in its own equivalence class because 2 minus 2 is 0 and 4 divides 0. What would the next element be?
Would it be 4?
What?
Would it be 4?
Okay, let's check it. What's 2 minus 4?
2.
And does 4 divide 2?
Yes.
No, it doesn't. 4 is bigger than 2. 4 can't divide into 2.
So would 2 be the only one in its equivalence class?
Jump by jumps of size 4. 2 plus 4. What's 2 plus 4?
6.
Now, so 6 minus 2 is 4, and that's divisible by 4, right? 6 minus 2 is 4, 4. And what's the next one? Keep going by jumps of size 4.
10.
Right. I mean, 2 minus 10 is -8, and 4 divides -8. 6 minus 10 is -4. 4 divides -4, right? What's the next one?
14.
Yep. And keep going until you get up to whatever the last one is in the set. Jumping by jumps of size 4. Keep going.
18.
And what about for 3? Well, 3 is going to be the first element in there. Always put the element in its own equivalence class. What next?
Would it be 6?
What's 6 minus 3?
3.
Does 4 divide 3?
No, so it would be 7.
Yeah. What's the next one?
11.
And then you keep on going until you. And what about 4? What will go in the equivalence class of 4?
It would be 4, then 8, 12.
16, 20. That's all for that one. But you need some more. I wish that helped me write what thing would go away. Does that make sense? So how many distinct equivalence classes are there?
Do I have to count up all the numbers inside the brackets?
No, you count the number of different sets. Notice this set and this set are the same. Oh, that should be it. 21. These two are the same set because they're in the equivalence class together. So their equivalence classes, see, 1 and 5 are both in there. So the equivalence class of 1 is equal to the equivalence class of 5 because they are related to each other. So that's one of them. And then the one for 2 is the second one. The one for 3 is the third one. And the one for 4 is the fourth one. There are 4. There's one for each remainder when you divide by 4.
Okay.
Now, the distinct equivalence classes would be, this one would be 1, so you can copy that and, put that in there. And then put a comma. And then this one, whatever it is, keep going. We need to keep adding some stuff to it, right? What would be the next number in the equivalence class of 2? Let's finish it.
18,
Good. What's the next number?
22.
Good. And that's it, because then we would be bigger than 24 if we wanted to try to put 26. So we can control C that, and put that one in here. I'm just using control C and control V, right? And then,
Yeah.
then we have to finish this one and put, whatever that one is, put it here, right? And then the last one is this one. It's a comma separated list of sets. Does that make sense?
Yeah, that does make sense.
Good. I'm glad you asked.
Will a question like this be on the exam?
Uh-huh. So practice with number 3, okay, yourself, and see if you can do it.
Okay, I will.
And these are very similar to the questions number 6 and 7 on the worksheet. So that was WebAssign number 2 and 3, right?
Yes.
Because number 2 is congruence mod 4. And so see also number 6 and number 7 on the worksheet. And see it, the class notes too. From
Okay.
day 25. Because we did congruence mod 4 on day 25. We did it on all of Z, not just a small subset of Z called A, but on all of Z. Okay?
Okay.
All right, ladies, it is 9:05, 9:03, and I've got to get going. I've got stuff I've got to do.